Let's say we have a function f of x is equal to sine of x, and we have another function g of x is equal to x squared minus 4. Certainly we know how to take the derivative of f of x. That would just be cosine of x. And certainly we know how to take the derivative of g of x. That would just be 2x. But what if we were given a function, and we'll call this f of g of x, which means take g and plug it into f. So that's going to give us sine of x squared minus 4. We have a function, x squared minus 4, that has been embedded into another function. In order to take derivatives that are more complex than these basic two functions, we need to learn something called the chain rule. And that's what we're going to talk about in this video. Okay, here we have a function, x squared plus 1, that is inside another function, something cubed or x cubed. So the process for using the chain rule is pretty simple, although it does get very complex as far as the type of functions you're going to have to take the derivative of, but essentially it's a three-step process. Take the derivative of the outside function, so you have to identify which function is the outside function. Leave the inside function completely alone. Don't do anything to it at all. And then multiply by the derivative of the inside function. So let's identify first of all, what is the outside function? Well, the outside function is something cubed. Let's just say it's x cubed. So if the outside function was x cubed, we would take the derivative just by using the power rule, and that would give us 3x squared. So let's go ahead and do that. Let's go ahead and take the derivative of the outside function, so that's going to be 3. We're going to leave the inside function alone. We're going to drop this power down because we are taking the derivative of the outside function, and then we are going to multiply by the derivative of the inside function, which is 2x. So once again, you have to identify which is the outside function. It's x cubed. What was substituted in for x? It was the other function, x squared plus 1. This is the inside function. So you take the derivative like you normally would. 3 comes in front, leave the inside function alone, drop the power down, don't forget to drop the power down, and then multiply by 2x. The chain rule is probably the most forgettable rule out of all the derivatives, so we want to make sure we understand it. Okay, let's see if we can apply the chain rule to these three problems. So we have something to the fifth. So the something to the fifth is the outside function. The inside function is 4x cubed plus 3x minus 2. So we will write f prime of x is equal to, we're going to take the derivative of the outside function, so that's going to be the power rule. So 5. Like I said, completely ignore this. Act like it's not there. Just rewrite it. 4x cubed plus 3x minus 2. Drop the power down because the derivative of x to the fifth is 5x to the fourth. Now we need to multiply by the derivative of the inside, which is going to be 12x squared plus 3. And essentially, that's it. There's not much more you can do. Move on to the next one. All right, here we have one with a fractional exponent. So y prime is going to equal 2/3. Leave the inside function alone. Drop the power down, so subtract 1. That's going to give us a negative 1/3. And then multiply by the derivative of the part that you left alone, so 4x cubed. Now let's see if we can write that a little bit better here. We have a 4 and a 2, so that gives us an 8 on the top. And a 3 is on the bottom. And we're going to go ahead and move this to the bottom, so that's going to give us x to the fourth plus 2 to the 1/3. And if we really want to get fancy, we can write it with a cube root. So it's going to be the cube root of x squared plus, x to the fourth plus 2. And there is your derivative. All right, let's look at this third one here. Here, we don't want to use the quotient rule because we can move this denominator up to the top. So we're going to rewrite this to be negative 7, 2x minus 3 to the negative 2. Now we're going to take the derivative. We're using the chain rule. Once again, we know we have to use a chain rule because we see a function 2x minus 3 that is inside another function. So we're going to do negative 2 times negative 7 is 14. We're going to leave the inside of function alone again. We're going to subtract 1 from the power, so you got to be careful and not add 1. And then we're going to multiply by the derivative of the part we left alone, which is 2. So that's going to give us 28 on the top and 2x minus 3 cubed on the bottom. Now we're going to get into some advanced techniques and advanced uses of the chain rule. This particular technique is called simplifying by factoring out the least power or the lowest power. So let's see if we can take this derivative here. We see that it is a complicated derivative because it's going to require the power rule and the chain rule. So let's see if we can do this. I'm going to rewrite this as x squared times 1 minus x squared to the 1/2 power. So let's start with the product rule. So we have the first, which is x squared, times the derivative of the second function. Now this is where we need to use the chain rule because the second function is a function inside another function. So we have to use the chain rule. So we're going to do 1/2, leave the inside function alone, subtract 1 from the power, don't forget that part, and then we have to multiply by the derivative of the inside, which is negative 2x. Now, you think you did a lot of work. We still haven't completed the product rule. All we did was the first function times the derivative of the second function. Now we have to do plus the second function times the derivative of the first, which is 2x. Put parentheses around that. All right, so let's see if we can clean this up a little bit. We have, before we start simplifying, we have a 2 here and a 2 there, and that's going to cancel out. And so that's going to leave us with negative x times x squared. That's going to be a negative x cubed, and 1 minus x squared to the negative 1/2 plus 1 minus x squared to the 1/2, and this is still times 2x. All right, so now what we want to do is we want to look for the least power that's common. So we have a 1 minus x squared to the negative 1/2 and a 1 minus x squared to the 1/2. We want to factor out, okay, I'm going to underline it here. I'm going to factor out the least power, the lowest power. So we're going to factor out of here a 1 minus x squared to the negative 1/2 power. That's the lowest power between negative 1/2 and 1/2. So that's going to leave us with negative x cubed. And then this gets a little tricky here. We have to think, if I take a 1 minus x squared to the negative 1/2 out, that's going to leave me with 1 minus x squared to the first. All right? Now, make sure you convince yourself of that. If I take this and I distribute this entire term here, this entire factor into this one, you add the exponents, negative 1/2 and 1, and that gets you back to a positive 1/2. So just be aware of that. And then there's 2x there. So let's see if we can continue over here. We have 1 minus x squared to the negative 1/2. And then we have inside of here a negative x cubed. And we have 2x times 1, which is 2x. And then 2x times negative x squared, that's going to be a negative 2x cubed. So that leaves us with negative 3x cubed plus 2x. And I'm going to move this to the bottom now, so that's going to be a 1 minus x squared to the 1/2 power. That's it. If we wanted to get a little bit fancier, we could put the radical sign back in, so it'd be negative 3x cubed plus 2x over the square root of 1 minus x squared. So you want to get comfortable with this factoring out the least power. It makes your simplifying a whole lot easier. All right, it's going to get more and more complicated here. We have a quotient rule that is going to be combined with the chain rule. This is going to get ugly. All right, so we're going to first, let's rewrite this without the radical sign. And let's write it as x squared plus 4 on the bottom to the 1/3 power. So let's use the quotient rule. If we want, just so you know, we could move this entire thing up to the top and use the product rule and change the exponent to -1/3. But I'm going to use the quotient rule just for practice. So we're going to take the bottom times the derivative of the top, which is 1, minus the top function, x, times the derivative of the bottom. So that's going to give us, now that's where we need to use the chain rule, 1/3, leave the inside function alone, subtract 1 from the power, which is going to give you -2/3, and then multiply by the derivative of the part that you left alone. All right, so we did the bottom times the derivative of the top minus the top times the derivative of the bottom, all of that over the bottom squared. Now, the bottom squared is just like taking the 1/3 power and raising it again to the second power. So when you have an exponent raised to another exponent, you multiply the exponents. So that's going to give us x squared plus 4 to the 2/3 power. Okay, so you can work that out on the side if that confuses you. All right, once again, let's see if we can clear some things up, make it a little bit cleaner. We have a 2x times x and a 1/3. So that's going to give us, let's just go ahead and copy down what we have here. And that's going to give us a minus 2x squared over 3. And let's see, 2x squared over 3, and then x squared plus 4 to the -2/3. Once again, this is very tedious work. It's not hard, but it is very tedious. And there we have it. Now, we're going to apply that same concept that we did on the last problem. We're going to factor out the lowest power. All right, let your eyes recognize x squared plus 4 is common to both. So I'm going to factor that out. I'm going to factor out an x squared plus 4 to the least power, which is this guy right there, -2/3. So I'm going to factor out this, and I'm going to put a bracket. And when I do that, I'm going to get x squared plus 4 to the first, even though I don't need these parentheses, but what I'm trying to show you is that if I take this x squared plus 4 to the -2/3 and multiply it times something that has a like base, the exponents will add together to get you back to 1/3. And after a while, you'll get comfortable doing this. All right, we factored out an x squared plus 4 to the -2/3 completely. So that's going to leave us just with -2x squared over 3 from this factor. And all of this is still divided by x squared plus 4 to the 2/3. All right, let's see if we can move this down to the bottom. So we're going to move this down to the bottom. When you move it to the bottom, it's going to turn the exponent into a positive 2/3. Then when you multiply it times this like base on the bottom that already has 2/3, it's going to give you x squared plus 4. You adding the exponents now, it's going to give you 4/3. So we have a 1, I'm going to put a 1 in front of this, a 1x squared and a -2/3 x squared. Those are like terms. So that's going to give you 1/3 x squared plus 4. And essentially we could multiply, we're pretty much done now, but to get rid of this fraction, we can multiply the top and bottom by 3. And when we distribute this 3 in, we are going to get a final answer of f prime of x equals x squared plus 12 over 3 times, let's just see, we'll just leave it as a fractional exponent for now, x squared plus 4 to the 4/3. Yes, it's a long problem, but this is the process you have to go through when you have a quotient rule combined with the chain rule. All right, let's see here. We have a fraction that is inside a squaring function. So we're going to have to use the chain rule. And so let's go ahead and do that. We're going to follow those 3 steps. We're going to identify the outside function as something squared. So we're going to do 2. We're going to leave the inside function alone. Leave the inside function alone. Drop the power down to 1. So essentially we have 2x to the first. Now we have to multiply by the derivative of the inside function. Ugh, that looks ugly because the inside function happens to be a fraction and it requires us to use the quotient rule. So let's go ahead and take the derivative of the inside function. So we have the bottom, x squared plus 3, times the derivative of the top, which is 3, minus the top function, 3x minus 1, times the derivative of the bottom, which is 2x. And all of that over the bottom squared. So x squared plus 3 all squared. All right, let's see if we can clean this up a little bit. So that's going to give us 2. And then 3x minus 1, x squared plus 3. And let's go ahead and distribute this in here. So that's going to give us a 3x squared plus 9. And then we have a negative 2x times 3x, which is going to give us a negative 6x squared. And then a negative 2x times a negative 1 is going to give us a positive 2x. And all of this is over still x squared plus 3 all squared. All right, let's see if we can simplify this further. 3x squared and negative 6x squared is a negative 3x squared plus 2x plus 9. And this is over x squared plus 3 all squared. And all of this is still times 2 and 3x minus 1 over x squared plus 3. All right, let's continue here. Tell you what, I'm going to make a little divider here so that we don't get lost. And so I'm going to distribute this 2 into here and make this a 6x minus 2. So essentially we have 6x minus 2 times negative 3x squared plus 2x plus 9. And all of this is over x squared plus 3 cubed, because x squared plus 3 squared times x squared plus 3 is going to give us cubed. So now we can distribute, and that's going to give us a negative 18x cubed, and then a 12x squared, and then we have a 54x, and then we have a positive 6x squared, and then a negative 4x, and then a negative 18. And so let's go ahead and group up our like terms here. I see negative 18x cubed does not have a like term. 12x squared and 6x squared going to give me an 18x squared. And then 54 minus 4 is going to give me a 50x, and then a minus 18. And all of this is over x squared plus 3, all cubed. And that is as far as you can take the derivative. Right, number 7, repeated application of the chain rule. So sometimes we have a function that is inside another function that is inside another function. So we have to use the chain rule more than once. So we have a sine cubed of 4t. I particularly don't care when they write the sign with the exponent here. So anytime it is there, I want you to get in the habit of rewriting it so that it looks like this. Sine of 4t all cubed. You're saying, why would you want to do that? Because now you can see what function is inside of what function, which is inside of what function. The 4t is inside of the sine function. The sine of 4t is inside of the cubing function. So we got to use the chain rule twice. So let's go ahead and do that. we're going to start with the outside function. So 3 comes in front. We're going to leave the inside function completely alone. We're going to drop the power down just like we normally would with the chain rule. Then we're going to take the derivative of the inside function. Well, the inside function has a function inside of it. So we're going to take the derivative of sine, which is cosine. We're going to leave the 4t alone, just like we normally would. And then we're going to multiply by the part that we left alone, which is 4. And that essentially is as far as you can go. So let's just clean this up a little bit. 4 times 3 is 12 sine squared of 4t times cosine of 4t. And essentially, that is as far as you can take the derivative. Example 8, we are going to learn how to use the chain rule on a problem that's essentially it's called parametrics. It's when you have 3 variables, x, y, and t. And so the idea here is in order to find dy dx, which is the slope of the curve of y, we have to take the derivative of y with respect to t, divide it by the derivative of the x function with respect to t. As we know, when you divide fractions, you flip the second fraction and multiply. So when you do that, the dt's are going to cancel, leaving you with dy dx, which is essentially what we want. So let's apply this to example 8. Find the equation of the line tangent to the curve x equals secant squared of t minus 1 and y equals tangent of t when t equals negative pi over 4. So we're writing a tangent line, so the same rules apply. We are going to need 3 things. We're going to need the x coordinate, we're going to need the y coordinate, and we're going to need m, the slope. Let's just go ahead and get x and y out of the way now. When t is negative pi over 4, you're going to plug that in to this x parametric equation to get the x. So x is going to equal secant of negative pi over 4 squared minus 1. Now, you can do this on your own. I trust that you're able to find the secant of negative pi over 4. That's going to be root 2. And so therefore, when you square root 2, you're going to get 2 minus 1, which is 1. All right, for the y, you're going to simply just plug in the tangent of negative pi over 4. So negative 45, so it's in the 4th quadrant. So the tangent of that's going to be negative 1. So we have our ordered pair. Our ordered pair is going to be 1, negative 1. What we're missing now is the slope of our tangent line. So we're going to go ahead and follow the little directions here. dy dt divided by dx dt. So dy dt is going to be simply the secant squared of t, which is the derivative of tangent. Now here's where the tough part comes in. Dx dt is going to equal, well, this is secant squared of t minus 1. So let's rewrite this like I did in the last problem as secant of t squared minus 1. Maybe that'll help you recognize that secant of t, not sect, but secant of t is inside another function, so we have to use the chain rule. So we're going to take the 2, bring it in front of this. We're going to leave the secant of t alone. We're going to drop the power down, and then we're going to multiply by the derivative of secant, which is secant of t tangent of t. All right, so that's our dx dt. So now we are going to take dy dt, which is secant squared of t, and we are going to multiply by the flip of dx dt, which is 1 over, and secant times secant is secant squared, so 2 secant squared t times tangent of t. And when we do this, we recognize that the secant squareds are going to cancel out, leaving us with a dy dx, because we have already divided dy dt by dx dt. Dy dx is going to be 1 over 2 tangent of t. Now we're going to plug in our t to get our slope m. So negative pi over 4 comes in here. So 2 times tangent of negative pi over 4. We've already done that earlier, and we found the tangent of negative pi over 4 to be negative 1. So our slope is going to be negative 1/2. Now we're going to write our tangent line. So our tangent line is going to be y minus our y coordinate, which is just 1, equals our slope, negative 1/2, times x minus our x coordinate. And this is a very long problem, but we've got the tangent line written. Okay, in example 9 here we have given a bunch of data. F of 3 equals 2, g of 3, f of 4, f prime of 3, g prime of 3, and all this extra stuff here. And we have h of x is equal to f of g of x. So g of x is the inside function, f is the outside function, and we need to find h prime of 3. All right, so in order to take the derivative of h of x, we need to first take the derivative of the outside function, so f prime. Leave the inside function alone. We're following the 3 steps of the chain rule. Times the derivative of the inside, which is g prime of x. There it is. I know it looks weird, but that's the answer. Now, h prime of 3 is going to be f prime and then g of 3 times g prime of 3. So let's see what g of 3 is. G of 3 is equal to 4. So let's replace g of 3 with 4. G prime of 3 is given to us as negative 5. Now f prime of 4 is given to us as 8. So 8 times negative 5 is negative 40. All right, here we have this last problem here. Find the points or point where the function has a horizontal tangent. So we know by now that that means that we need to set the derivative equal to 0. So let's go ahead and do that. So we're going to use the quotient rule. Let's go ahead and rewrite this as f of x equals x over 2x minus 1 to the 1/2. So we're going to take the bottom, which is 2x minus 1 to the 1/2, times the derivative of the top, which is 1, minus the top, which is x, times the derivative of the bottom. Now this is where the chain rule comes in again. So we're going to have to do 1/2, leave the inside function alone, drop the power down to a negative 1/2, and then multiply by the derivative of 2x minus 1, which is 2. Now, a couple things we can do to clean this up. The 2 cancels with that 2, and let's see what we have here. 2x minus 1 to the 1/2 power, and then we have minus x to the 2x minus 1 to the negative 1/2 power, and all of this is over the bottom function squared. Now remember, the bottom function is originally a square root, so when you square a square root, it just goes away. So maybe I'll write this as 2x minus 1 to the first. Now I'm going to factor out the least power again. So I'm going to factor out, because we see a common term, 2x minus 1. So I'm going to factor out the least power. So 2x minus 1 to the negative 1/2 is going to be factored out. And that's going to leave us with 2x minus 1. And right now, I'm going to put this in parentheses, although I don't need to, just so that you can see that if you multiply this back in, the exponents will add together and get you back to 1/2. Okay, minus x. And all of this is over 2x minus 1. Now I'm going to move this to the bottom. And when I do, it's going to combine with this exponent and become 2x minus 1 to the 3/2 power. And here we have 2x minus x, that's x minus 1. And we're going to set that equal to 0. And we know any fraction is equal to 0 when its numerator is 0. But just in case that's confusing, let me just go ahead and multiply both sides by 2x minus 1 to the 3/2 and 2x minus 1 to the 3/2. When we do that, this is going to cancel out with that. Essentially what we're going to have is x minus 1 equals 0. So the only point on this graph where the slope is 0 is at x equals 1.